And we continue with another installment in our series on basic analysis of rational functions. This is the next example that we have teed up right here, and as in other installments, the instructions are the same. Basically what we're being asked to do here is to determine any intercepts that this rational function has, find any asymptotes that it has, and tell the domain and range. So first order of business, as with the prior example, you got to do some factoring here. And so if you take a look at what you're going to get, let's see. Now the numerator is a difference of squares pattern, believe it or leave it. And it's going to factor initially as x squared plus 4 and x squared minus 4. The denominator, common factor of x, it's going to be x times x minus 2. Now hopefully you would notice that the second quantity in the numerator, the x squared minus 4, is again difference of squares. And so if you factor completely, you're going to have x squared plus 4, x plus 2, x minus 2, all of that over x times x minus 2. So as with the prior example, we have a common factor, namely x minus 2, that can be canceled. And we will cancel it, but it's important to remember that you can only make that cancellation happen if the rational function is well defined to begin with, which means that when you make that cancellation, there's a tacit assumption that x is not equal to 2. Because if x was equal to 2, then you would have 0 divided by 0, which would be undefined. And so you have to be aware of that restriction right out of the gate. So in terms of a final form of this, you have a couple of choices. You could write it as x squared plus 4 times x plus 2 over x, and that is a rational function. You may want to find a different way of writing that, though. But anyway, let's answer the questions that they asked us, and then we'll get to that. So the first thing they're asking us is intercepts. And so we had mentioned previously, intercepts come from different locations. The x-intercepts occur where the numerator of the rational function is 0. And so x squared plus 4 is never going to be 0 for any value of x. But x plus 2 will be 0 at negative 2. And so depending on what your learning management system wants, sometimes a single value or sometimes an ordered pair, you could also say that this is negative 2 comma 0. Now the y-intercept, that's going to come from capital F of 0. So in other words, you're going to take that rational function, you're going to evaluate it at 0. Now in this case, you can see that it's undefined at 0, actually, because the denominator is x. And so it's undefined, and there's no y-intercept. So there's the intercepts. Let's talk about asymptotes. Now we normally go after vertical asymptotes first, and as we have mentioned a number of times, vertical asymptotes occur where your denominator is 0. And so we can say right by inspection that the vertical asymptote is going to occur at x is 0, which is another name for the y-axis, and so you'll see that when we graph it. It's going to have a horizontal asymptote. Well, no, it doesn't have one of those either. And the reason is something we've mentioned a number of times as well, because we said that, hey, when the degree of the numerator is greater than the degree of the denominator, which is the case here, regardless of the form you're looking at, you will not have a horizontal asymptote. And so if you wanted to justify this, you could say that the degree of the numerator is greater than the degree of the denominator. Kind of my abbreviated way of indicating that there. Now it does have a slant or oblique asymptote. And so you could abbreviate that SA or OA depending on how you want to go. I'm going with SA this time. Anyway, how do you find that slant asymptote? Well, I hate to tell you, but you have to do a little bit of polynomial division in order to get that. And it's from the quotient. And so I'm going to say that in English right there. Now, again, from my perspective, the slant asymptote is not a hugely important thing, because it's mainly an artifact from back in the day when you had to graph one of these rational functions and there was no graphing calculator or computer. And so having knowledge about how to find the slant asymptote was helpful at that time, because it could help you to quickly sketch the rational function. But here, we have readily available graphing technology, and so we're less reliant on that. We can get a graph much more easily. But if you insist on having it, again, it's of minimal interest in our course, but people get upset. They get confronted sometimes by questions in the learning management system, and they want to answer them. It's totally understandable. We can go off of the simplified version of this that you see right here if you want to quickly analyze that, but you're going to need to do probably a little bit of expansion in the numerator first. So let's make some space and we'll chat briefly about this. Let me work off to the side here, and then we'll make use of that space. So, if you expand the numerator there, x squared plus 4 times x plus 2, you're going to have x cubed, and you're going to have 2x squared. You're going to have a 4x and an 8. And because we canceled that common factor, you're really dividing by a monomial, namely x. And so it's not really legit like polynomial division in the usual way we think of long division. It's more like divide and conquer. So in other words, you could rewrite this as x cubed over x, and then 2x squared over x, and 4x over x, and 8 over x. And the slant asymptote, or the oblique asymptote, however you want to describe it, is going to come from the quotient of that division, which would be this part right here. And so if you continue to simplify that, you're going to end up with x cubed over x is x squared. 2x squared over x is 2x. 4x over x is 4. And then you're going to have 8 over x. So the 8 over x is technically the remainder of that division, and it's the quotient that we're interested for this, the oblique asymptote, x squared plus 2x plus 4, right? Now, how that's going to look, well, you have to see the graph in order to catch a glimpse of that. And so, anyway, we'll show you the graph because we need to talk about the domain and the range. But let's do one thing at a time here. So the next thing that we would mention would be the domain and range, right? Now the domain is easy enough. If you saw the prior installment, you realize that we inherit that restriction of x not being 2. And so that's going to be reflected in the domain, but we also have to avoid having x being 0 because it makes the denominator 0, which makes the rational function undefined. So the range is kind of easy. It's going to be, let's label it first. So it's going to go up to to 0, and then it's going to break. And it's going to go to 2, and it's going to break, and then it's going to go to positive infinity. And as far as the range is concerned, well, it's much easier if you look at the graph when you do ranges, and so let's do that. I think I took the liberty of keying this in. Let me see. I did. And I keyed it in the unreduced form. It doesn't really matter what form you key it in. Whatever seems good to you is fine. In fact, if you wanted to verify that I did the division correctly, if you're skeptical or whatever, you could put in what I got as the quotient there, right? And the remainder, of course. You just have to make sure you key it in right. And you'll see that these two graphs coincide exactly. So we have x squared. We have 2x and 4, and then we said that our remainder, which we're going to need in parentheses so that it digests, would be 8 over x. So it's going to graph both of them at one time, and just to avoid confusion, I'll turn off that one, and then I'll zoom 6 it, standard zoom. So there's the graph, and it's tricky to see that slant asymptote here because the graph isn't zoomed out enough. So I'm not sure that I want to graph that part. I guess I could. It wouldn't be that hard. Let's graph the other version and show you that they're the same. Where y equals, and I'll turn off the first one, and I'll turn on the second one there. There you go. See, it looks the same, right? So if we'd graphed them both at the same time simultaneously, you wouldn't have been able to see both of them, I think. So anyway, where does that slant asymptote come in? Let's go back and fix that so you can see how that works. So I have the original function there. I got to turn it back on. I forgot. Turn it on there. Oops. And then in order to get that slant asymptote to display right, let's delete the remainder, the 8 over x. So we're only going to be graphing the polynomial portion of that, which is the quotient, like we were saying, right? Whoops, I hit the wrong key. Try that again. Don't judge too harshly. You'll be middle-aged too one of these days. Okay, there we go. Let's graph it now. So that's how the slant asymptote works on this one. We already knew that we had an asymptote at the y-axis, right? That's the line x is 0. And so that's what's kind of governing the behavior on the so-called bottom half of the graph right there. The top half, though, sticks to that slant asymptote pretty closely, and you can see that if you zoom out a little bit. Let's open up the y values so we can better see how that plays out. Let's go to like -25 to 25, and then let's make the scale 5. That should be good. Let's see how that looks. So there was another piece of this function actually that we weren't seeing because we weren't sufficiently zoomed out. And that's why this is such a great example, because many people are content to use their calculator, just at a very low level, let's put it that way. And so it never occurs to them that something outside of the default view might be of interest. And this is such a great illustration of that, because once you zoom out, you realize, oh my gosh, there's another piece of this function which I would have completely missed had I not looked around a little bit. And so that's why this is such a rich example. But you can see what we want here. You can see, of course, how the slant asymptote meshes with this. And the slant asymptote is not always a line. In this case, it's not anyway. And so this is a very excellent, rich example. Now, the only other question we have to answer here before we quit this and go to the next installment would be, what about that range? Now, it may look superficially like we have a gap in the range here, but we don't. And the reason is that when you look at the left half of the function, if you will, you can see that that graph covers the entire y-axis. It goes from -infinity to infinity. So it's going to spit out every possible value of y. And in terms of answering that, let's go back to the iPad here. The range is all real numbers. Stay tuned for the next installment.